Okay, we thank Dr. Kanhori for his presentation. And now, ladies and gentlemen, it's my pleasure to introduce Dr. Saeed Monir, an esteemed expert in the field of structural engineering. With a wealth of knowledge and experience, Dr. Monir has made significant contributions to the advancement of structural engineering. His expertise spans a wide range of topics, and his insights and research have helped shape the infrastructure of tomorrow. Please join me in welcoming Dr. Saeed Monir.
Hello, everyone. Good evening. My name is Saeed Monir, and first of all, I wanted to take this opportunity to thank and express my gratitude to scientific committee, especially the Professor Khalou, who hold this conference and give this opportunity to us to share our research. My talk is about multi-scale simulation of CFRP composite structures under thermomechanical loading. This is a very interesting topic and has been recently in the forefront of different engineering strengthening fields, and especially in the reinforced concrete structures. As we all know, numerical methods are indispensable part of any engineering problem, and today I'm going to talk about a very effective and special technique in solving CFRP composite structures. In our research, we have investigated the multi-scale computational homogenization, which is a very robust technique in solving different heterogeneous media. Well, carbon fiber reinforced polymer composites, or CFRP composites, are widely used in several engineering applications, including aerospace structures, astronautical structures, high-pressure vessels, and also in the reinforced concrete structures in order to strengthen different elements. These composites are composed of fibers, carbon fibers, embedded inside epoxy resin matrix. It is worth to note that these fibers are anisotropic and have different behavior in different directions, and these epoxy resins are considered to be simply isotropic materials. Well, as you see, these are the advantages of these CFRP composite materials. These remarkable properties makes these composite materials highly attractive for strengthening different structural elements. Let's explore these properties, specific advantages of these CFRP composites. Firstly, their exceptional strength to weight ratio, which allows them for significantly strengthening different structural element without adding excessive weight to the structure. Secondly, the high stiffness to weight ratio, which is as a result of elastic modulus, it enhances integrity of concrete structures under different loadings. And also, these composite materials offer exceptional durability and also very, very superior resistance against corrosion, resulting in long-lasting performance. Well, we discussed about the advantages of these materials. So now we are going to talk about the disadvantages and the issues and challenges. So these materials offer undeniable advantages for structures. However, when they are exposed to harsh environmental conditions like elevated temperature, in the case of, for example, fire, they lose some of their strength and the stiffness. This is what we call the reduction in the strength and stiffness. So this is when these composites are exposed to, for example, in the buildings, are exposed to fire, which is the main focus of our study. Also, the combined effect of moisture and high temperature can reduce the strength and the stiffness of these kinds of materials, and even these kinds of conditions can change the thermal properties of these materials, like thermal conductivity, which can affect its performance. Well, we discussed about the disadvantages. Now we are going to talk about what we have in the practical problems. In the practical problems, most of the studies, most of the engineering, designing methods, designing and analysis methodologies do not consider the effect of these composites when these structures are faced with the fire, for example, or harsh environmental condition. They ignore the presence and existing of these composites because of their complex behavior. This is where a great need for robust numerical analysis arises for capturing the effect of these composites. So among all of the numerical methods, you know that the finite element method is known to be the most powerful method in analyzing different complex geometries and complex material behavior. However, in the case of CFRP composites and also other heterogeneous domains, we know that these heterogeneities and the fibers have very small dimensions, which is around 5 to 10 micrometer. In order to accurately capture the effect and behavior of these carbons and these carbon fibers and heterogeneities, we need to consider very fine mesh, which significantly increases the computational costs, and so most of the times we cannot perform such analysis on normal computers. We may need some supercomputers with high memories, or most of the times even with the supercomputers with high memories we cannot perform such analysis. So equivalent models are proposed where a simple rule of mixture is used to volume average the properties of these materials to derive a unique material with equivalent properties. In this case, we use these equivalent properties in the finite element method, but however, we reduce the computational cost, but we lose the accuracy, and we will show in the numerical results that even with this method, we can't actually capture the effect of damage, effect of crack propagation, or other failure mechanism because we cannot capture the real behavior of these materials. So I'm going to introduce the multi-scale methods that can capture and can analyze these kinds of heterogeneous media without increasing the computational cost and effectively solve any kinds of heterogeneous media, especially the CFRP composites. The first one that I'm going to introduce is the asymptotic homogenization approach. This approach is semi-analytical numerical method, but cannot capture the complex behaviors because of its limitations, and also it's not able to predict the transient effects. So we go through the next method that is known as computational homogenization method, which is a very robust technique and can overcome the limitations of the previous one. This method can capture the complex behavior of these heterogeneous media, and we are going to talk about this method and apply it on the CFRP composites. So in this slide, I'm going to very briefly explain about the procedure of computational homogenization approach. I'm not going to go deep into this method. It has many details, mathematical and theoretical details. I'm not going to mention them. Just general explanation about this is enough in this session. Consider a heterogeneous domain like a CFRP composite that we are going to study. This domain is subjected to thermal and mechanical loading. So we consider a similar homogeneous domain with the same geometry and with the same boundary conditions, as you can see in the figure. But the material behavior of this homogeneous domain is considered to be unknown. For any material point in this homogeneous domain, we associate a microscale domain which accounts for the heterogeneities of the domain. This microscale domain is called representative volume element, or RVE. These RVEs represents the heterogeneities of the domain. We transfer some information from that macroscopic point to the microscale domain. We evaluate the boundary value problem in the RVE. After the solution is completed, we calculate some information like stress and elastic modulus or other quantities that we require, and transfer them back to the macro scale level in order to use in the simulations. It is worth to note in this case, we do not directly calculate the stress from the strain. We calculate it from another domain known as the microscale domain, or RVE. Very briefly, I'm going to explain the governing equations of thermomechanical processes. As you see, the governing equations include a stress equilibrium equation and the energy balance equation, which accounts for conductive heat transfer inside the composites. You see these two equations and PDEs are coupled together through the thermal strain, which is shown on the left of the screen, and these are solved together in a coupled manner. Any computational homogenization approach has two steps. The first step is downscaling. We should transfer some information from the macro scale level to the micro scale level, or RVE. In our case, we transfer the macroscopic displacement field and temperature field and their gradients, namely strain and temperature gradients, to the RVE, and also we define an unknown field known as fluctuation fields to be defined in the boundary value problem of RVE. We also impose some linking constraints in order to ensure the consistency of these fields, and which results in some boundary constraints which should be satisfied by appropriate boundary conditions. This is very crucial stage. I'm not going to explain more about this topic, but we have one should be careful about applying choosing the appropriate boundary conditions, because we have to transfer some effects like transient and dynamic effects, which is crucial here in this stage. So the next step is the upscaling stage, which we equate the energy in the macro scale point with the volume average of the energy inside the RVE or micro scale domain. This will ensure the consistency of our solution, and we can derive the boundary value problem from these equations, and also we can calculate the quantities like stress and also the elastic modulus and other quantities from these equations. So we transfer them back to the macro scale level, we put them in the boundary value problem of the macro scale, and we can solve the general problem. You can see the algorithm of transient computational homogenization. We start from the macro scale level, we loop on the elements, we loop on the Gauss quadrature points, and we, for any Gauss quadrature point, we move down to the microscale level and we solve the boundary value problem, and we calculate the effective properties like elastic modulus or stress. We transfer them back and we construct the stiffness matrix and Jacobian matrix and residual vector, and we continue this procedure until we reach the convergence and steady state condition. We arrive at the numerical results section for validation of, for the purpose of validation of our model. We have chosen a heterogeneous beam, a benchmark problem that is a heterogeneous beam composed of fibers embedded inside the matrix, which is shown in the top, on the top of the screen. This beam is loaded thermally and mechanically on its right edge, and we have solved it with our proposed multi-scale method, and the results are in good agreement with the results reported by the reference, and also we have shown the transient effect captured by our method in the bottom right side of the slide, as you can see, in comparison to the steady state solution. So we arrive at thermomechanically loaded CFRP composite slabs. Consider a slab that is fixed at its both ends, and it is loaded from its top surface. The temperature of the top surface is increased. Due to the symmetry, we solve only the half of this slab. So the left side is the middle of the main, left side of this slab that you see is the middle of the main slab. So the dimensions are obvious. The diameter of fibers is considered to be 7 micrometer. The load, the distributed load is increased from 0 to 100 Newton per square meter in 10 seconds, and it is kept constant until the a steady state solution is achieved, and simultaneously the temperature of the top surface is increased by 190 degrees, and in 10 seconds again, and it is kept constant until the steady state solution is achieved. The thermal and mechanical properties of the materials are given in this table. Now, you see the results of our simulation in comparison to the conventional equivalent models, which is relevant in the practical problems. You see that our multi-scale analysis differ significantly from the equivalent models, which shows that these equivalent models cannot capture the real and true behavior of these kinds of structures. And these are the variation with time of horizontal force at the support and the moment at the support. And also other results, you can see vertical displacement of the middle of the slab, temperature, and also moment versus the displacement at the middle of the slab. The nonlinear behavior of these materials can be completely seen from these figures, which are completely captured by our proposed method. And finally, we have chosen one fiber at the middle of the slab with its round matrix, and we have plotted horizontal stress distribution inside these fibers and at different time instants, as you can see. At all time instants, you can see the fibers are in compressive conditions while the matrix is completely in tension. Well, you can see that the equivalent models which do not consider any distinction between these the fibers and matrix cannot capture this effect, which is very crucial when we want to capture and detect some phenomena like damage or crack propagation or other failure mechanisms. And you can see the equivalent values relevant in the conventional equivalent models versus in comparison to our calculated homogenized models, which you can see that there are significant difference between these values. As a closure, we proposed a multi-scale procedure for thermo-mechanical analysis of CFRP composites. Nonlinear behavior of thermal and mechanical properties are captured. And also, the effect of microscopic transient terms can be included in this model, and the superiority of this approach with respect to the conventional equivalent models is demonstrated. Thank you for your consideration.
Do we have any questions from the floor? We can have one question. Well, let me ask the question, one question at least. So if you want to expand it to structural elements, such as beams or columns, I mean, do you have to take further steps to expand actually the knowledge that you have, or whatever you have now, you can actually, based on those, can reach a conclusion?
Yes, actually this there's no limitation in our formulation. Actually, it is extended to any structural member, and there's no limitation for, in the basis of our formulation and the results actually. You can see that we have solved this lab. We have solved this lab that it can be a structural member, and we are going to solve, we are going to extend this to different defects in the structural composite structures, which is the very relevant in the structural analysis, the debonding of these CFRP composites from the reinforced concrete beams, for example, in the harsh environment. We are going to extend these formulations for the case of defects and damage, including the debonding conditions and different damage evolution.
So due to the limited time that we have left, because we have to give back the salon to the people who have actually are responsible for actually this salon. So we will limit our tea break to 10 to 15 minutes. Maximum 5 minutes? Okay. So the previous actually speakers extended their lecture. So we have no other choice but to limit ourselves to the 5 minutes for the coffee break. Thank you.